Okay, so let's return to properties of the delta function. So last time we discussed what happens when inside of the delta function, the argument of the delta function is another function. So we discussed the example when we have the integral of the delta function depends on x squared minus 4 dx. So in this case, the delta function will be non-zero when the argument of the delta function is 0. So it means that when you plot this delta function as a function of x, it will be non-zero at 2 points, x negative 2 and 2. And near this point, we need to write down the argument, just looking at the coefficient or the terms which are linear at this point. So it means that near this point, we write down the x squared minus 4 is a x minus 2, x plus 2. So x is 2, so this term is 0, so we need to keep this as a 0. This should be replaced as a constant, because near x equals 2, this will be just constant. So it will be just 4 x minus 2. Similar at this point, it will be negative 4 x plus 2. So this is the idea how to deal with the delta function argument, when the argument of the delta function is another function. So as a result, this integral will be, we divide this integral into integrals from negative infinity to 0, from 0 to infinity. So as a result, last time we discussed, it will be 1/4 plus 1/4, so it will be 1/2. Now let's consider a little bit more complicated case when the argument of the delta function is another function, not more complicated general form of the delta function. So let's consider that argument of the delta function is some function g which depends on x dx. So the question is, what will be such type of integral? So at first we need to look what is the profile of the delta function g. So we plot g as a function of x, and we are looking at the points at which function g is 0. So for example, this is our function g, goes like that. So we're looking at these points 1, 2, 3, 4, and 5. Then we divide this integral from negative infinity to infinity into integrals from negative infinity to this point, which include point number 1. Then from this point to this point, which includes point number 2. Then from this point, for example, to 0, which includes point number 3. Then from this point to this point, which includes point number 4. And from this point to infinity, which includes point number 5. Okay, then near each point, we write down this delta function as we use the Taylor expansion, because the function g, we write down this function g using Taylor expansion. So function g is, at this point is 0. And then, for example, at this point it will be g. Near this point it will be 0, because function is 0. And then we keep the first non-zero term, which is the linear term. So it will be derivative of function g with respect to x at point 1. And this will be x minus x1. So you can see this is just some constant. So it's similar to what we did in the previous example, when we extract some constant and then multiply by something which goes to 0 through this point. And then we can easily calculate the integral, because it will be just constant multiplied by x minus x2. So we can easily calculate the corresponding integral. It will be just constant, 1 divided by this constant. So when you calculate the integral from negative infinity to this point, this term gives us just 1 divided by absolute value, because this can be positive and negative. Absolute value derivative of function g with respect to x at point 1. Similar when you calculate the integral near this point. Again, we use the Taylor expansion near point 2, and we write down g near point 2, it will be 0. And then we calculate derivative, so we will use a linear term in the Taylor expansion, x minus x2. Again, calculate the integral near this point, so it doesn't matter what is the limit. The most important is that you need to have this point at which the delta function is infinitely large inside of this interval. And this integral gives us 1 divided by this constant. So it will be 1 divided by absolute value derivative g with respect to x at point 2, so on and so on. So it will be the sum of all these terms, and finally the last term will be 1 divided by absolute value derivative of g with respect to x at point 5. So this is the idea how to calculate this type of integrals. So we divide this, at first we identify the points at which the argument of the delta function is 0. So the points at which this function g is 0. Then near this point we use the Taylor expansion, because at this point the function g is 0, so we can use just linear term in this Taylor expansion. And then we can calculate the corresponding integrals and so on. Of course, in this case, we can have some special cases when the first derivative is 0. So it's very non-trivial case. For example, it means that we have delta function of the following shape. Delta function which depends on x squared dx. Something like that, integral. So you can see that in this case, if you look at delta function is 0, argument of the delta function is 0 at point x equals 0, but we don't have the linear term. So it's a quadratic term. So it goes like that. And the question is how to calculate this type of integral. So in this case, we need to be very careful. So we need to look exactly what is the physical meaning of this delta function. So it's not physically, it's not a single point. Physically, it has some finite size. And in this case, to calculate this type of integrals, at least in physics, we need to use some kind of approximation of the delta function in terms of Lorentzian, or in terms of Gaussian approximation, something like that, or in terms of step-like function. And then you need to calculate the corresponding integral, and then calculate the limit when the width goes to 0. Usually, considering this type of limit, if it is some kind of physical problem, you should get some finite result, physical result. But again, in this case, we need to be very careful. There are not many such type of problems. You need to be very careful how to deal with this type of integrals. So we need to consider delta function as a limit of some kind of approximation, some Gaussian or Lorentzian shape, and then calculate this type of integrals. Now, so this is how we calculate the integral delta function, and the argument of the delta function is another function. And if you have some more complicated expression, we have delta function g of x, and then multiple times another function f dx, something like that. So the idea is the same. At first, we need to identify the points at which the delta function is non-zero. For example, similar to this example, argument is non-zero. Argument of the delta function is 0. So following exactly the same steps, but now at each point, near each point, for example, near point 1, x1, we write down this function g, use the Taylor expansion, and near this point, function f will be just the function at point x1. So it means it will be very similar to this expression, but this extra coefficient will be f at point x1, f at point x2, f at point x5. So the expression will be f x1 divided by absolute value of g, derivative of function g with respect to x at point x1, plus and so on, f at point x5, absolute value of function, derivative of function g at point x5. So this is the idea how to calculate the delta function with this type of arguments. So this is a delta function of a single variable. So it's one-dimensional delta function. We can generalize this expression for two-dimensional and three-dimensional delta functions. For example, when you consider three-dimensional delta function which depends on radius vector r, by definition, the three-dimensional delta function, sometimes we can introduce some index 3, which means it's three-dimensional delta function, and there are different notations. But the means that three-dimensional delta function depends on the vector. So r is a three-dimensional vector. So by definition, it has the following structure: delta function, one-dimensional delta function which depends on x, one-dimensional delta function which depends on y, and one-dimensional delta function which depends on z. And each of these delta functions are defined as a one-dimensional delta functions. So this is a structure of this definition of the delta function for three-dimensional case, and similar for two-dimensional case, and so on. So this is a delta function. In this case, you need to be careful when you, for example, do some transformations. For example, if you have delta function of 3r, and you calculate the integral of this delta function over dx, dy, dz, then it will be, because it's a product of three delta functions. So you need to be careful how to extract this coefficient 3. It's not 1/3. It's 1/3 times 1/3 times 1/3. Because it's product of three one-dimensional delta functions. So to be integral of delta 3x, delta 3y, delta 3z, dx, dy, dz. And then for each one-dimensional delta function, it will be 1/3. 1/3, 1/3, 1/3. So finally the answer will be 1/3, 1/3, 1/3. So you need to be careful how to deal with this coefficient. So it's a product of three one-dimensional delta functions. So again, the delta function is very useful object. It describes the properties of a point charge. And usually when the size of this charge or the size of the object is very small compared to the distance to this object, we can consider this, describe this object as a delta function. So in application to electricity, delta function describes the charge density. So this is what we discussed last time. So when you write down the charge density, so the charge density describes the point charge. It depends on the radius vector r. So describe in terms of the, for example, point charge q 0 to the delta function r minus r0. So it means that delta function is three-dimensional delta function, which is non-zero when r is equal to r0. So another way expression will be like that: q0, one-dimensional delta function x minus x0, one-dimensional delta function y minus y0, one-dimensional z minus z0. So this is a delta function of a point charge. Now, another useful property of the delta function is the Fourier transform of the delta function. So let's look at the Fourier transform. So Fourier transform is, by definition, if you remember definition of Fourier transform in general, Fourier transform of any function. Let's consider one-dimensional case. So function f depends on x. So we calculate Fourier transform. So it will be f as a function of k. So it will be integral fx exponent I kx dx. So let's call this, put some tilde. So it means it's Fourier transform of function f. And we calculate the integral over x from negative infinity to infinity. And sometimes people put some extra factor here, for example, 1 divided by square root of 2 pi, or 1 divided by 2 pi. This is not really important, but this is a Fourier transform of any function f. Now let's look what is the Fourier transform of delta function. For delta function, we calculate Fourier transform, which depends on k. So it will be 1 divided by square root of 2 pi integral delta function, the function of x, I kx dx, and we know the property of the delta function. Then, so it's product delta function with other function, another function. And when you calculate this integral, we just need to substitute x equals 0 in this another function. So finally it will be just 1 divided by square root of 2 pi 1. So you can see Fourier transform of the delta function will be constant. So this is a property, interesting property of the delta function. And then using the property of the delta function, that when you calculate the inverse Fourier transform, so it means that delta function of x should be 1 divided by square root of 2 pi integral of Fourier transform of the delta function exponent negative I kx dx dk. So inverse Fourier transform. Then if you substitute Fourier transform, this is 1, or 1 divided by square root of 2 pi. Then you can see that you have the following identity. So it will be 1 divided by 2 pi integral I kx with negative sign dk. So it's interesting representation of the delta function in terms of the integral. So you can see we calculate the integral of this exponential function over k. It will produce delta function of x. It's very non-trivial property. So it means that we can express the delta function as a function of x as a 1 divided by 2 pi integral exponent negative I kx dk. Negative or positive, it doesn't matter because delta function is even with respect to x. And we calculate the integral from negative infinity to infinity. So the reason why it is has this property that if, for example, x is non-zero, then we have the integral of the oscillating function, because this is the exponential function, the cosine and sine function, with non-zero argument. So it means that this is the integral of the cosine or sine function, so the average will be 0, we have equal number of positive and negative values. So it produces 0 values, so it means that when x is not equal to 0, it will be 0. When x is 0, this exponential function will be 1. So it will be integral from negative infinity to infinity dk, so it will be infinity. So as a result, it has the correct properties. That will be 0 when x is non-zero, and infinity to large when x is 0. So this is an interesting representation of the delta function in terms of the integral. Again, we use a lot this type of representation, and for some applications, because it's when you do the transformation to the different Fourier transform in the different reciprocal space or direct space, for example, in the solid state physics, we do this type of transformations, these identities. Now another representation delta functions, different coordinate systems. Because remember, we introduced the spherical and cylindrical coordinate system. How can we write down the delta function in different coordinate systems? So let's look at the following expression. At least from this expression, we define the delta function in different coordinate system. So charge q, point charge q, which is localized at a given point. So this point is characterized by the x, y, and z, for example, coordinates. Or by, in terms of the cylindrical coordinate system, it will be rho, some point rho prime, for example, c prime and z prime. This is the position of the point charge. So we can write down the simple identity, because the point charge will be integral over d rho, d psi, dz q. This will be integral rho minus rho prime, integral psi minus psi prime, integral z minus z prime. Okay, this is identity, because this is how we define the integral. Integral of delta function over rho gives us 1, over psi gives us 1, over z gives us 1. So this is identity. So we write down this expression for the charge at a given point, localized at point rho prime, psi prime, and z prime. Now I want to rewrite this expression in the correct variables, because we know that the element of the volume in cylindrical coordinate system is not d rho, d psi, dz. This is the element what we use for dx, dy, dz. This is correct without any coefficient. But for cylindrical coordinates, we need to introduce rho here. And then effectively it means that we need to divide by 1 over rho to make its identity, correct identity. And now we have the correct element of the volume in cylindrical coordinate system. So it means that the charge density in cylindrical coordinate system should be defined through this expression. So it's not just the product of the delta function, it's 1 over rho and the product of the delta function. So this is the charge density in cylindrical coordinate system. So the charge density in the rectangular, regular Cartesian coordinate system, the charge density will be q delta x minus x prime, delta y minus y prime, delta z minus z prime. So it's straightforward expression. In cylindrical coordinate system, you can see we need to introduce this extra 1 over rho coefficient, because we need to have the correct property. We calculate the integral of the charge density over volume, and when you calculate the integral, we need to introduce this rho coefficient here. So charge density in cylindrical coordinate system will be q divided by rho, and now we have rho minus rho prime, delta psi minus psi prime, delta z minus z prime. So it's the charge density in cylindrical coordinate system. So you can see we need to be very careful how to define the charge density of a point charge in terms of delta function in different coordinate systems. Similar way, we can write down the expression for charge density in the spherical coordinate system. So we use the same identity. So the integral over r, theta and psi in two angles. So it will be q delta function, because we have some sense we have just three one-dimensional integrals. Delta function r minus r prime, delta function theta minus theta prime, supposition of the point charge psi minus psi prime. And then again, we need to write this expression in the correct form. So it will be charge density, rho, and this should be the element of the volume in spherical coordinate system. But this is a wrong expression, so we need to introduce some extra factors here to make it element of the volume. R squared sine theta. R squared sine theta, so it means that in this case we need to divide by R squared sine theta to make it identity. So we need to introduce extra vector R squared sine theta. So finally, the charge density in the spherical coordinate system will be q divided by r squared sine theta, delta function r minus r prime, delta function theta minus theta prime, delta function psi minus psi prime. Of course, in this expression, you can see we have the factor r squared sine theta because it's a product with the delta function. We can replace this r by r prime, because it will be non-zero only at one point when r is equal to r prime. So effectively, it will be exactly the same if you put prime here and theta prime here. Similar in this case, because the product is a delta function which will be non-zero only at one point when rho is equal to rho prime, we can put rho prime here. So it's the same identity. So this is how we define the delta function, or the charge density of a point charge in cylindrical and spherical coordinate system. And this is a Cartesian coordinate system. So you need to be careful, so it's not just the product of delta function. We need to have introduce this extra element related to the volume in the corresponding coordinate system. Another property of the delta function is that this is what we'll use later on in electricity. So this is the delta function again. The delta function described as a point charge at a given point, and in this relation, another way to introduce the delta function is a Laplacian over 1 over r function. So let's look at this another expression. The delta function can be also described as a Laplacian over 1 over r minus r prime. So it's a delta function at point r prime, localized at point r prime. So we can calculate this Laplacian, and if you go straightforward, if you calculate this Laplacian, so this is what we discussed last time, if you calculate this Laplacian at any point r, so it will be 0 if r is not equal to r prime. So it means that we need to be very careful to what happens when r equals r prime, because at this point we have singularity, and we need to calculate this very carefully, this Laplacian. So it is if you go straightforward, if you introduce the spherical coordinate systems, this is what we discussed last time, so we will go to 0 for this expression. We calculate the Laplacian of this 1 over r function, it will be 0. So it means that we need to deal somehow with the singularity at r equals r prime. So we can calculate, for example, a more simple case when r prime is 0. So it will be a similar expression. We calculate the Laplacian 1 over r function. So if you go straightforward, if you introduce the spherical coordinate system, then you can easily calculate that using the spherical coordinates. So it will be 1 divided by r squared, derivative over dr, r squared, derivative over dr, 1 over r. So this derivative gives us 1 over r squared with negative sign, so it will be just 1 over r squared derivative 1, which is 0. So you can see this Laplacian 1 over r is 0 at all the points except r equals 0. So to calculate this, what happens exactly at r equals 0, so it means that at a singular point, we have some singularity at the origin of coordinate system. So to look at the singularity, we just need to calculate the following, introduce some small volume. So I want to just calculate the integral around the singularity. And then we calculate this integral. So we use the Gauss theorem and write down the following expression. So I calculate the integral over this small, so introduce the sphere around this point and calculate the following integral. So it will be element of this spherical coordinate system, so it will be r squared dr. Then it will be integral over sine theta d theta d psi, and this will be the Laplacian of 1 over r. So calculate the integral around this point. So I use the Gauss theorem, so I don't calculate this explicitly, this type of volume integral. I write this expression, what we discussed for the Gauss theorem, in terms of the flux. So you can write down this Laplacian as a product, as a divergence of the gradient. So in this case, you can see I calculate the divergence of the following vector field. And then I got the following expression. So this will be the flux of this vector field through the surface, of the sphere. So it will be integral over volume of this divergence of this vector field. So this vector field A. So it will be the flux of this vector field through this surface. So it will be integral r squared, integral over angles. So it will be, let's call this solid angle. So this is a combination, it's called the solid angle. And this will be the flux. So it will be unit radius r, which is exactly the direction of the normal. Direction of the normal is the unit vector r, or we can call this direction of the normal. And this will be gradient of 1 over r. So we need to calculate this exactly at the radius, at the surface of this sphere of radius r. So we need to calculate exactly when r is equal to r. Now the gradient, so at this point r is not equal to 0. So we can easily calculate the gradient. So this will be, if you calculate this gradient, it will be r, unit vector r divided by r squared. So you can calculate this gradient. Again, do, for example, explicit calculations in x, y, and z variables, or use the spherical coordinates. So you can see it's r unit vector r divided by r squared. And then this r and r gives us 1. R squared will cancel this r squared. So finally it will be with negative sign when you calculate this gradient, because it's 1 over r, derivative 1 over r gives us extra negative sign. So finally it gives us negative 4 pi. 4 pi comes from the integral over solid angle. So it's integral over all possible theta and psi. This integral gives us 4 pi. It's a solid angle. So finally we can see on the right hand side we have the so we calculate the flux. So this is a vector field, and we calculate the flux of this vector field over this surface of the sphere. And on the left hand side we have the volume integral of this Laplacian, or we can write down in Cartesian coordinate system as a dx, dy, dz, Laplacian of 1 over r. So you can see we calculate the integral of Laplacian, which is 0, but it is not 0 only at one point, maybe 0 at one point, r equals 0. And we get the final result, non-zero result. So it means that this term, which is non-zero only at one point, should be delta function at this point, at point r. Delta function with respect to x, y, and z. So finally, from this expression, we derive that the Laplacian of 1 over r should be, this is a coefficient, so it's coefficient in front of the delta function, should be negative 4 pi delta function of rho, three-dimensional delta function. So it's another expression for the delta function as the Laplacian of 1 over r. And you can see it's very non-trivial fact how to extract this delta function. So if you calculate explicitly these derivatives, then you can see this derivative gives us 0, but we have some singularity at r equals 0. So it means that we need to somehow extract the singularity, And in this case, to extract the singularity, we need to calculate the integral around this point, because it's a property of the delta function. Then the integral with the delta function should be constant, should be 1. So it means we can extract this type of singularity. So we use the Gauss theorem. So we calculate the integral over volume of this function with the delta function, with the Laplacian of 1 over r. And we rewrite this Laplacian as a divergence of the gradient of 1 over r. So then we can consider this a vector field. And we use the Gauss theorem. So we write this integral as a flux of this vector field, so the surface of this sphere. So finally, in this case, we can easily calculate that this integral will be non-zero, it will be negative 4 pi, because we can easily calculate this gradient of 1 over r, it will be r with negative sign, unit vector r divided by r squared. So we need to substitute r equals r capital. Then finally, we derive the following expression for Laplacian.